Okay, so in this lecture, we look at a concept called conformations, so conformations of molecules. So conformation is just the precise arrangement of atoms in space. And so conformational isomers then are molecules that differ only by bond rotation in the molecule. So you can't move you can move atoms in space, but only by rotating around bonds. You can't break an atom off and put it somewhere else. All that you can do is take a molecule and rotate around a bond, and that creates different conformations. Okay, so that's our first example. So we'll take ethane, for example. So ethane, of course, is CH3. So if we draw the expanded structural formula out and show all of the bonds, then ethane looks like that, but that's not a good representation of what ethane looks like because each carbon is sp3 hybridized, so it's tetrahedral. Right, so each carbon is tetrahedral, and so if you remember what a tetrahedron looks like, right, that's a tetrahedron, where each of the bond angles is 109.5 degrees. Okay, so each of these carbons in ethane is tetrahedral. So if we want to try to draw a three-dimensional structure on a two-dimensional piece of paper, then we can use what's called a sawhorse projection, or we could use a dashed wedge projection. So we could draw what the molecule looks like in three dimensions like this. So if you remember what the solid wedge means, that means that atom is coming out of the page, and the dashed wedge means that the atom is behind the page, for example. Or if I had the molecule, so let's see. So this would be how I have the molecule drawn on paper. So if you took the laptop and held it straight up, so if we're looking at it like that, so if you took your paper and held it straight up in front of you, then this is what it looks like. So we have a hydrogen that's coming straight up, down to a carbon, over to a carbon, and down to a hydrogen, and all of those are in the same plane. Right, those four atoms are in the same plane. And then you have a hydrogen coming towards you, and a hydrogen coming towards you, and so those will be on a solid wedge. From your perspective, from my perspective, they're going away from me, so they would be on the dashed wedge. And then this hydrogen is coming towards me, and this hydrogen is coming towards me. So from my perspective, that would be on a solid wedge, but from your perspective, it's going away from you. So those will be on dashed wedges if you drew it from your perspective. Okay, so that shows what the molecule looks like in three dimensions. And so we'll often draw molecules. So this is where organic chemistry gets difficult for a lot of students. It's a very visual subject. And if you can visualize what these molecules look like in your head, organic chemistry becomes a whole lot easier. Okay, so that is what this molecule looks like. And so what we're going to do now is we're going to draw what's called a Newman projection. So if you can picture yourself standing over here, and you're looking at the molecule from this perspective. So you got to picture yourself standing over here. So here's your head, and you're looking at the molecule like this. And your feet are down here, right? You're standing on the ground, your head's here. And so this would be your left hand, and this would be your right hand from my perspective. And then this would be towards your head. So if we draw a Newman projection, then the front carbon looks like that. So that's the carbon. So that's the carbon atom. And then you have a hydrogen towards your head. And then if I'm standing over here looking at it like this is my right hand. So this is on my right hand, and this is on my left hand. So if I'm standing here looking at it like that, so if I'm looking at it like this, right, this is my left, this is my right, and this is towards my head. And then, so we keep the same perspective to look at the back carbon. So if we look at the back carbon, we represent it with a circle. So that's the back carbon. So I drew that in the wrong spot. Let me move that. It's going to be in the way. Okay, so again, if we're looking over here from this, so then this hydrogen here is towards our feet, right? Because our feet are down here. So we have a hydrogen going towards our feet. And then we have a hydrogen, so this hydrogen is in between these two hydrogens. And you can see that if we look at it from this perspective. All right, so if you're looking at it from that perspective, there's your heat, there's your head. And, all right, and on the back, that one's towards your feet. So we said this was our right. So this is our right, and so this is on our right. So that's projecting up here. And this was on our left, and this is on our left. So that's projecting up here. So that would be a Newman projection of this molecule, looking at it from that perspective. Right, you could have just as well stood over here and looked at the molecule. So if you're standing, so you always look between the wedge. So if you're standing there looking between that wedge, so if you're on the right side of the molecule looking at it from that perspective, then your front carbon looks like a Y. And your back carbon looks like an upside down Y. All right, so this is looking from left. And this is looking from the right side. Okay, so now what we want to do is, so in reality, molecules rotate around single bonds extremely fast. So the molecule is constantly sitting here doing that. And of course, these atoms are moving in space as well. So it's constantly rotating around that bond. It's flipping around over in space. And it does that, rotates around bonds several 100,000 times per second. So extreme molecular motions are extremely fast. Okay, so what we're going to do is we're going to take this Newman projection. And so first of all, if we look at it, so from this hydrogen to that hydrogen, it's about a 60 degrees. And so when the molecule is in this conformation, it is said to be in a staggered conformation. And so what we're going to do now is rotate. Around the carbon-carbon bond, 60 degrees. So we're going to keep one of the carbons fixed. So let's keep this, so this carbon, you're looking at it from that perspective, so we're going to keep this carbon fixed, and we're going to rotate around the back carbon 60 degrees. So then it goes like that. So now the hydrogens are behind each other. This hydrogen in the back is behind that one, this hydrogen is behind that one, and this hydrogen is behind that one. So if we rotate 60 degrees, keep the front carbon the same, rotate the back carbon. We'll draw them slightly skewed so that you can see it, but in reality it is, so basically what we're doing is we're looking, instead of looking at the molecule straight on where you can't see the back hydrogen, we're just looking at it slightly skewed like that so that you can see the back hydrogens. Right, but if we look straight on, it's hard to see the hydrogens behind because they're directly behind the other hydrogen. Okay, and then if we rotate 60 more degrees, keep the front carbon the same, rotate the back carbon, then we go, so we went from staggered, this is what's called eclipsed. I don't think I'm spelling that right, let's try again. Oh my gosh. So it's an eclipse conformation. That's when the atoms are directly behind each other. And then 60 more degrees, we're back to staggered. So for ethane, then there's really just two conformations. It's either staggered or it's eclipsed. So if we looked at an energy profile, so first of all, which do you think is more stable? Do you think it's more stable for it to be staggered or more stable for it to be eclipsed? And the answer is it's more stable to be staggered because atoms like to have space. If it's eclipsed, then they're closer together in space, and you have what's called steric interaction. So that would typically be symbolized using that symbol. So that's a destabilizing interaction. So if it starts at some energy staggered, so if we call this A, and then it moves to B, and then it moves to C. So if that's A, then it goes to staggered. So that's B, and then it goes back down to C, back down to staggered. So there's only 2 conformations for ethane. And if you rotated 60 more degrees, of course, you would go back to another eclipse conformation. Okay, so let's make the molecule more complex. So let's take that off, and let's take that off. So this orange ball could be anything. It could be 2 chlorines, it could be 2 methyls. So maybe this is now CH3, CH2, CH2, CH3, or maybe it's chlorine, CH2, CH2, chlorine. So maybe it's butane, or maybe it's 1,2-dichloroethane. The energy profile is going to be similar. It's going to have similar conformations. So we're going to start in this conformation where the 2 chlorines are furthest apart as possible, or the 2 methyls if it's butane. So we're going to basically look down this bond. We're going to look down if it's butane. We're going to, so if we number this 1, 2, 3, 4, we're going to look down C2, C3 bond. Or for 1,2-dichloroethane, if we're looking down this bond, then we would be looking down C1, C2 bond. Okay, so let's just make this dichloro. Well, let's make it butane. Now let's make it 1,2-dichloroethane. And let's draw this as a dash wedge structure. Okay, so if we were standing over here and we drew a Newman projection, let's make them happy. So this chlorine is towards your head, so it's going to be on top, and then this hydrogen, so if you're standing here looking at it from this perspective, this hydrogen is on your left. It's on my left anyway, right? And this hydrogen's on my right. So this is on my left, and this is on my right. Not that it matters, because they're both hydrogens, you can't tell them apart. And then the back carbon, so if I'm standing here, my feet are on the ground, so this chlorine is towards my feet. So it looks like that. So it's a staggered conformation. And in this case, 2 biggest groups. Are the furthest apart. That's called the anti-conformation. Okay, so what we're going to do is let's rotate 60 degrees, draw that. Let's rotate 60 degrees, draw that. Let's rotate 60 degrees, draw that. Let's rotate 60 more degrees, draw that. That's 60, 120, 180, 240, and then we'll go 60 more degrees, draw that, so 300, and then 60 more degrees, draw that, so 360. We'll be back to where we started at. Okay, so we're going to look at it from this perspective, so we're going to rotate that so that you can see it from that perspective, and then we're going to rotate the back carbon clockwise 60 degrees, so then it goes to an eclipse conformation. So we'll keep the front the same, rotate the back. So this hydrogen goes behind that chlorine. This hydrogen goes behind that hydrogen. And this chlorine goes behind that hydrogen. So now we have eclipsed. So we'll call this A, we'll call this B, and then 60 more degrees. So then this chlorine's going to rotate in that space, this hydrogen will rotate into that space, and this hydrogen will rotate into that space. So we're going to take that now and go 60 more degrees. So now we're back to a staggered conformation. And then we're going to go 60 more degrees. So now the chlorine goes behind the other chlorine. And then 60 more degrees. So now the chlorine comes between the chlorine and hydrogen on the front. Right, 60 more degrees. Now this chlorine goes behind that hydrogen, and this hydrogen goes behind that chlorine, and this hydrogen goes behind that hydrogen. And then 60 more degrees, 360, now you're back to where you started at, right? Okay, so A, B, we'll call this C, we'll call this D, we'll call this E, call this F, and we'll call this G, which equals A. Now let's sketch the energy profile. Okay, so the most stable conformation is the anti-conformation, where you have the two biggest groups farthest apart. Right? So chlorine's a lot bigger than hydrogen atom is. So they want to be as far apart as possible. Okay, so A is here, and then we go 60 degrees, and then 120, 180, 240, 300, 360, we're back to where we started. Okay, so when we go from A to B, does the energy go up or down? So when we go from there to there, does the energy go up or down? Well, it goes from staggered to eclipse, so the energy goes up. So that's 0. So energy goes up when we go to B. And then we go to C, it goes back to staggered, so the energy goes back down, but does it go back down all the way to A? So is C as stable as A? And the answer is no, because the two chlorines are getting closer in space. So this type of interaction is what's called a gouge interaction, when two things are 60 degrees from each other. So it goes back down in energy, but it doesn't go down all the way to A. So that's C. And then when you go 60 more degrees, now the two chlorines are as close together as they could possibly be. So that's going to go back up in energy, and it's going to go up higher than B, right? So D is going to be higher in energy than B because the two chlorines are closest together. So that's D. And then when you rotate 60 more degrees and go to this, well, that conformation is equal in energy to this conformation, right? Because all of the interactions are the same. So E is equivalent in energy to C, and you're back to a gouge. And so D is eclipsed, the least stable eclipsed. So 60 more, you go back down in energy, equivalent to C. And then when you go 60 more degrees, then that's going to be equivalent to B, because you have two hydrogens behind each other, and then two hydrogen chlorines interactions that are eclipsed. So that will go back to being equivalent to B. So F, and then when you go to G, you're back to where you started at, 360. Okay, so if this was two mouthfuls, it would be the same energy profile. Just the energy gaps will be a little bit different. Okay, so hopefully that made sense. So if you have 1,2-diachloroethane, it can exist in all of these conformations, all right? But if you had 1 million molecules, for example, and you could freeze everything out and and count all of the different conformations, most of the molecules would look like that in the AntiConformations, and the fewest amount of molecules would look like that, eclipsed. And then you would have the second most predominant structure would look like that or like that, which are equivalent to each other. But at any one time, majority of the molecules are going to be in an AntiConformation. So if we wanted to sketch the eclipsed in a dashed wedge structure, so if we took this and we went, how many degrees? 60, 120, 180. So if we rotated 180 degrees around the bond, if we keep the front carbon the same and rotate the back carbon, then it would look like that, right? Where these are eclipsed and these are eclipsed and these are eclipsed, because those are both back and these are both front, so they're eclipsed, and those are both on top, so they're eclipsed. Okay, so what I might ask you to do, for example, is let's draw hexing looking down the C3 C4 bond, and most stable and least stable conformation. Okay, so hexane is obviously 1, 2, 3. Oops. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. So we're talking about looking down the C3-C4 bond. So when it's drawn like that, the molecule does not show three-dimensional aspect to it, right? But so what you have to recognize, okay, so C3 needs to be in front. So what all is attached to C3? Well, C3 has two hydrogens attached to it, and it's got an ethyl group attached to it. And what does C4 have attached? It's got two hydrogens attached, and it's got an ethyl group attached. So we need to draw a Newman projection. So that's the front carbon, and if it's going to be most stable, then it's going to be in a staggered conformation, right? So this is going to be most stable. And if it's going to be least stable, then it's going to be in an eclipsed conformation. Okay, so the C3 is in the front, C4 is the circle in the back. So C3 is attached to C4, but we don't see that bond, right? Because that's the bond between the front vertice and the circle in the back. What we see is the other three things. We see the two hydrogens and the ethyl group. So we can put the ethyl group wherever you want to put it. We'll just stick it on top. And then the C3 has two hydrogens. And then C4 in the back has an ethyl group. And it's got two hydrogens, right? So that would be the most stable conformation, or drawn as a dashed wedge structure. It would look like that, where the two ethyl groups are 180 degrees apart. Okay, and if we wanted to draw the least stable structure, then CH2, CH3 there. And on the back carbon, CH2, CH3. And then each carbon has two hydrogens, right? Or that would be like that, right? So it doesn't matter to me. You can use the line formula, or you could write out the atoms, whatever you prefer. I understand both structures, so whichever one you feel most comfortable drawing is the one that you should draw. Obviously, drawing the line formula is easier. It requires less writing, so you can do it faster. But if it helps you to see all of the atoms, then by all means, draw out more of an expanded structural formula, but put it in 3 dimensions. So if I ask you to draw most or least stable, then you're going to have to use a Newman projection like this, or you're going to have to use a dash web structure like that, because that is how you illustrate 3 dimensions in organic chemistry. Okay, we'll stop there.